Yeah, so welcome back, Professor Shubhabrata Das, Presidency University will deliver its third lecture on small cancellation theory. Yeah, over to you, Shubhabrata.
Okay, thank you. So we were discussing about small cancellation groups, and we saw a few different small cancellation conditions, and we introduced small cancellation metric, small cancellation condition C prime lambda, which says that pieces are lambda small compared to the relators. That means this. We also introduced other small cancellation conditions like both combinatorial in nature, like CP and TQ conditions. So I haven't mentioned those in this recap today because we will mostly not go into those directions. Little bit at the end. So these are the small cancellation conditions, but the main use of small cancellation that we saw is in solving the word problem for C prime 1/6 groups, which was facilitated by this some sort of primitive Greenlinger lemma, we may call it. I mean, Greenlinger lemma, the actual lemma is giving us much more. This is a more elementary claim, but it is enough for us to satisfy the prerequisites to run the dense algorithm. Now, we saw the proof of this fact last time that if we have a word representing the trivial element, then we will have subwords which are part of another defining relator where that subword u is greater than half of that other relator. So that was quite useful thing. This facilitated the dense algorithm, which we discussed last time. And then we saw that essentially the same thing is giving us linear isoperimetric inequality, which is this. The combinatorial area of the Van Kampen diagram corresponding to this freely reduced relator is less than the length of the word. So since the linear isoperimetric inequality, if a presentation satisfies a linear isoperimetric inequality, that group, if a finitely presented group satisfies linear isoperimetric inequality, that is Gromov hyperbolic. Now, since from the discussions that we had last time, we can see that a group with C prime 1/6 small cancellation presentation, it satisfies linear isoperimetric inequality. It is Gromov hyperbolic. So that's roughly the what we talked about last time. And today we want to go back to the statement of to the Rips theorem that we talked about last time, maybe the last time. So Rips theorem, maybe it will be better appreciated now. This is a theorem which is saying that given any finitely presented group G, we can construct another finitely presented group gamma, which gives G as a quotient with the kernel, a normal subgroup, N, finitely generated. Okay, So this was a remarkable statement because we see that G can be any finitely presented group. We have not mentioned any restriction on G apart from just being finitely presented. And what we are saying here is that we can construct a group gamma which gives G as a quotient group. That means, are we not saying that all finitely presented groups can be seen as a quotient of a C prime lambda group? And moreover, lambda is also arbitrary. So suppose, I mean, here what we are essentially, I haven't written it here, but what we mean is lambda is less than 1/6. So it's written just lambda is less than, greater than 0. But I should mention here that we want lambda to be less than 1/6. So for such a lambda, if we can construct a group gamma, which is a small cancellation group, giving G as a quotient, that and G is arbitrary, that means for an arbitrary lambda less than 1/6, if we have a group satisfying C prime lambda, we can get any finitely presented group as a quotient of that small cancellation C prime lambda small cancellation group gamma, right? So that is a remarkable statement which says something called SQ universality of small cancellation groups, that we given arbitrary finitely presented groups, they can be retrieved as a quotient of this kind of groups. But what we want to do today is see a little bit about the way this group is constructed, and the details will be done in the tutorial. So last time I mentioned this group, I did not mention what kind of relators I will choose, because the choice of relator is the main important thing. You see that if I start with this group G as S1 with R1, S1 generating set and R1, the relators, then suppose this is the presentation. What we are doing is we are generating this group with two extra generating elements. We are generating this new group gamma with two extra generating elements. We will have to produce some relators for this group so that this group satisfies this small cancellation condition, C prime lambda small cancellation condition. Now, how to get that firstly? So we have to choose the relators suitably. Now, one thing let's see first, that if we take the generating set like this, x1, x2, xn, the same thing as S1, and this A and B, what we are doing is from this group gamma, we are sending the map to G by sending all these generating elements to themselves identically and sending A and B to 1. And now we can see that the kernel is generated by A and B, and the kernel is a finitely generated normal subgroup. And we have to show that this presentation gives us C prime lambda small cancellation presentation. How to do that? So other things about this result are more or less understood, I believe. That that we have a group like this is more or less, I mean, it is believable so far, because the other things seem feasible. Only thing that you may need to ask is the presentation C prime lambda, and how to ensure that. Now, you see the relators here were R1, R2, Rm, and the relators we have considered here is R1 star. Here star is something which I haven't mentioned. What is star? We'll see. But for the set of relators, what we are taking is R1 star, R2 star, Rm star, these relators, and then for each generating element from S1, we are considering Xi. So we are conjugating the other two generating elements. We have two new generating elements, A and B. What we are doing for the other set of generators is we are considering, we are conjugating A with Xi's and Xi inverses and multiplying them with those words, those typical small cancellation words, if we may call them. So one set of relators is R1 star to Rm star. Another set of relator is conjugates of A with Xi and Xi inverses, product with a small cancellation word, and another set of relators being conjugates of the other generating element B with Xi's and Xi inverses, product with small cancellation words. So this set of relators will satisfy C prime lambda condition if the pieces are lambda small. Now the question is, this is the set of the relators, and what can we choose for star, so that, and we can visibly see here our eyes have no reason to satisfy small cancellation conditions, because G is an arbitrary finitely presented group is uh, which is not necessarily a small cancellation group. So our eyes themselves, they don't have any reason to satisfy C prime lambda conditions. So, and for the other sets of relators, this and that, also these conjugates, these are just small words, right? So length 3 words, xi inverse or xi inverse a xi. So these are just small words. So if there has to be any small cancellation, that has to come from star essentially. So a close look at these set of relators tells us that if we can ensure sufficient small cancellation inside the word star or words star, then essentially everything falls into place, right? So if star is a sufficiently small cancellation word, then this entire set will satisfy C prime lambda condition, right? Any question so far? Okay, so then now the question becomes, what can be a choice of star? So For a choice of star, we can take a word, maybe say we take a word in these new letters A and B, because these words, these letters A and B, these will be sent to the identity. So we take a small cancellation word, maybe say, let us look at something we talked about last time as well, I guess. Uh, say a b square, a b cubed, a b to the 4, say up to a b to the 100. Now, if I take this small cancellation, if I take this word, we had talked about certain words, certain subwords as the pieces in this. So, does anyone recall? Excuse me. Uh, does anyone recall that we talked about certain subwords as pieces here? So, what can be possible pieces here? Is B a piece, or B a B square a piece? See that B a B B a B square appears here, and also B a B square appears here. So B a B square appears at least twice in this word in two different ways. So that is a piece, right? But based on that, can we say that this word satisfies C prime lambda small cancellation condition? No, because we may have larger subwords like these, which subwords like this, which are the pieces, and they are much longer. So if we have to ensure that we satisfy C prime lambda, then we have to look at the largest pieces, and we saw the largest piece in this expression would be, say, b to the 98, a b to the 99. So this would be a word which has two different occurrence in this word, and there is no other word longer than this, a subword of this word, which appears twice in two different ways in this. So this is the largest piece in this context. This word is the largest piece in this context, and its length is what? Its length is say 198. The length of this word is 198. So what is the length of this word? This is a much longer word, right? So its length is 100. So its length is more than 5,000. So that is more than 20 times this length, right? So we, when we talked about this example, we said that this relator satisfies a small cancellation condition of C prime 1 by 20. Now, suppose we take this word and put this word here at the place of star. Then what will happen if I take this word and put it here? So I have, how many relators do I have? I have say M relators coming from these M relators, and I have how many, say, 2n relators coming from all these conjugates product with star. So total I have 2n plus m relators here. on these n plus 2 generating elements, and what are the pieces. Now you see that if our eyes satisfy our eyes in any way satisfy certain small cancellation, that is anyway good. But if even if they do not, these are finitely many words of finite lengths, right? So uh, I can certainly choose this number suitably, this 100, so that I can I can have the length of this word suitably large and length of these subwords, the pieces, suitably small compared to them, so that the common subwords, the pieces may or may not, which are appearing, may or may not appearing in our eyes, length of those pieces won't simply matter. So I will take this word star in such a way that all the pieces appearing in these will dominate the pieces appearing in our eyes, and these won't matter in any way. So for all these twice n plus m relators, we can see the largest pieces can be made to uh, appear in only these small cancellation words, not in the other things, right? And once we can ensure that, then what we have to show is that the pieces that those are appearing in these subwords, these words in the relators, they are suitably small. And that we can see that if we take words like this, and there can be different choices regarding such words, and we will see those things in the tutorial. But more or less we can understand by that by choosing words of this form or something similar, where uh, very long common subwords are not appearing. You see that by taking different powers of b and interjecting them by a, we are killing the possibility of having very long subwords which appear twice, right? So uh, that is the essence of this entire theorem. Ripp's theorem, it has a lot of consequences, but the idea of the proof is very basic. That if we can put everything in this form, then the pieces would be as small compared to the relators as we wish, and by doing that we can make it a c prime lambda presentation. And then we can say that c prime lambda presentation, since it is hyperbolic, we can get these g's as a quotient of hyperbolic groups with finitely generated kernels and so on. So there are many consequences of Ripp's theorem, which I won't be going into, but there are many remarkable consequences of Ripp's theorem, and it's a very important theorem. I just wanted to discuss the idea of the proof and the importance of having the small cancellation words present in the relators, so that the pieces we can, the lengths of the pieces compared to the relators, we can control and make it a c prime lambda presentation. So that is more or less what I wanted to talk about Ripp's theorem today, that how we can make it c prime lambda. Now one other example I would like to talk about. I won't talk anything about the theorem as such. So this is a theorem proved by Baker and Riley. This was an answer to a question asked by Mohan Maharaj, and this is a negative answer to that question. The question was, if we have a hyperbolic subgroup of a hyperbolic subgroup H of a hyperbolic group G, whether in all cases the identity map, the inclusion of H in G continuously extends to the boundary of H to boundary of G. So the question was answered negatively with this example. And what is the statement, what is the theorem saying is that if we have positive words, so by positive words we mean that no negative power of the generating elements are appearing in these words. Okay, so no negative powers of the generating elements are appearing in these words. So if we consider positive words C, C1, C2, these three on C1 and C2, and D1, D2, D11, D12, D21, D22. So how many here? 6. So these 3 and these 6 on, so these 6 on D1 and D2 and these 3 on C1 and C2. So if we have these relators, okay, so if we have these, if we have these positive words, and if we have a group G generated by A, B, and the C1, C2, D1, D2 with the set of relators R, where R is these words. What are those? A inverse B inverse AB is C, B inverse CIB is CI, that is B inverse C1B is capital C1, B inverse C2 B is capital C2, and so on. You can see the words. So now what they are saying is that this group will be hyperbolic. This is a subgroup of this group H. Is the cursor visible? That I'm moving the cursor, is it visible today?
No, no.
No. Okay. Okay. So is this visible that when I select it?
Yes,
Yes.
yes.
Okay. So what the theorem is saying is that if we consider this group generated with these elements, so the generating elements for these words, generating elements for these words, D1 and D2, and A and B. Okay. So, and then if we consider the relators like this, then the group is hyperbolic. First claim, and the second claim is that the subgroup generated by B and D1 and D2, so this subgroup that is generated by B and D1 and D2, that is a subgroup of G. It is a free subgroup of rank 3 of G. So H is also hyperbolic, right? It's a free group of rank 3. So we get two hyperbolic groups, G and its subgroup H, which is also a free group. What they claim is that there is no Cannon-Thurston map for this pair. So this H subgroup of G, this pair, there is no Cannon-Thurston map from delta H to delta G. That is what they are claiming. We will not go into the proof of this theorem that there is no map like this, but what we would like to talk about is how they get this group G, and what essentially are they doing to prove that this group is hyperbolic. This is not the entire, this is not the only important thing that they are proving. There are other things. They talk about distortions and other things, but this is one of the main part of the proof, that to construct a G like this, which is hyperbolic. And to show that G hyperbolic, they are again here, I'm sorry, there's a misprint. This would be C prime 1/6 SCC, small cancellation condition. So this is a typo. This one is a typo. So what they are doing essentially is, let us take a close look at the relators, at the positive words they have taken, because essentially the relators are constructed with these words, right? So you see that this first relator is A inverse B inverse AB is equal to C, and if I want to write it as say C times AB, say C times the inverse of this, right? So B inverse A inverse B A, then that would be a relator, right? The other two relators are, oh, okay, there is another misprint here. Sorry, very sorry. So this would be less than or equal to. This would be less than or equal to I. Both I and j are essentially, what we are saying is I and j are 1 and 2. So this is a misprint. So what are the relators here? The relators are C times the inverse of this, C1 times the inverse of this with C1 here, C2 times the inverse of this with C2 here, then D1 with the inverse of this with D1 here, and similarly D2 with inverse of this with D2 here, and so on. And Dij's, so 4 of them, Dij's with these inverses. Now, if we recall, then it looks very similar to these things, right? In this case, we had certain words juxtaposed by big small cancellation words, right? These words finally were these words were almost inconsequential. Whichever our eyes we may have here, or these conjugates, they have no role to play as such in regards to the pieces and their lengths relative to the words and so on. So these words look very much the same. The relators here in this group also looks very much the same, right? So if in place of these C1 C2 D1 D2 D1 1 1 2 D2 1 2 2, all these words, if we can choose them suitably, then it appears that from this presentation G should satisfy certain small cancellation condition. If we can choose these 9 words C1 and 2, then all these D, I, J's, etc. What are the choices they have made is, look at these words, C carefully. Even the cursor is not, I'm unable to select it. So, okay, sorry. Anyway, if we look at C, what is C? C is C1, C2, C1, C2 square, C1, C3 cubed up to C1, C2 to the R. Now you see that this is the exact same word we talked about yesterday and today, right? So this is a typical such word where pieces are small compared to the actual word. Now you see that if I consider the word C1, C2, C1, C2 square, C1, C2 cubed, if I just consider this much, now does it satisfy C prime 1/6? Will this relator satisfy C prime 1/6? It will not, right? Because here for this word, the pieces that it has compared to the length of the entire word are not that small. So what we have to do to in order to make those words smaller, make those subwords smaller compared to the length of the word is we have to keep taking such products. So why are we interjecting these c2 square and c2 cube by a c? So that the pieces cannot become very long. Because you see, when you have a c1 here and a c2 to the 4 here, you see that if you have uh, if you take this portion in common, say c2 square c1, then c2 squared c1, and then c2 cubed. If you want to go till c2 to the 4, now you see that this word, this subword, doesn't occur at a different place anywhere in this word. Suppose I go till c2 to the power 50. Now, can you see another occurrence of this word in this big relator? Can we find another occurrence of this subword c2 square c1 c2 cubed c1 c2 to the 4? We do not find this word a second time. That means this cannot be a piece. Why? Since this was interjected by these c1s and I have a c2 to the power 3 in between, that c2 to the 3 prevents, because if this c2 square and c2 to the 4 has to if I have to take those things ever again, suppose I take c2 to the 30 c1 c2 to the 31 c1 c2 to the 32 c1 and so on. Now I can take a c2 to the power 4 here, and the rest would be c2 to the 28 c1, right? Here you have a c1. Suppose I make this as well c2 square, and then I make the remaining as c2 to the 28, and then there is a c1. Now you see that we have c2 to the c1, then c1 c2 to the 4. We can find them at other places, but what is there in between? In between there is a c2 to the 31, and we cannot find a c2 to the 3 in between, however much we try. So this is the beauty of this choice, that this choice is essentially forcing us to have shorter common subwords. I mean, subwords which has multiple occurrences in this big word. So that is essentially saying us that the pieces are small compared to the actual word, the big word. Fine. So we can see in all of these, here R is arbitrary. We can increase R as much as we wish in order to make the pieces small. Now you see that Ci means C1, C2, both are taken this way. So what is C1? C1 is C1, C2 to the R plus 1. Then, and this way you go up to R plus R, that is 2R, right? So here you are starting from R to and going to 2R. Then C2, what is C2? C2 is C1, and then C2 to the 2R to C2 to the 3R, right? Right? So these are CIs, and then DIs. How are you choosing DIs? DIs are D2 to the, say, D1, then it would be D2 to the R plus 1 to D2 to the R plus R. That means you're going from R to R. So similarly for D2, you will be going from say d2 to the 2r to d2 to the 3r. Now for dij's, you are going from, say, now you have chosen L to be another fixed number. So we are going from, say, suppose I and J both have 1, then you are going from RIL to RIL plus, sorry, sorry, I said wrong. You are going from RL to RL plus R, right? And for J and for the other choices, you can see very well that it's the same word. I mean, it's a word of the same pattern, and since it is of that pattern, we are having the pieces essentially of this form. So pieces will be small compared to the words if we increase R. So I'm trying to say the same thing again and again, only to emphasize that this choice of the words are giving us so important results, and they are giving us many beautiful constructions. So it doesn't seem as such that it is essentially, so there must be something that we are not able to figure out from these things, uh, which can be generalized. So, is it only about manipulating words like this and finding this kind of some pathological words, and where such subwords pieces are small compared to the word length, and only in such cases things work? No, one thing we will see in the tutorial that these choices may vary, and given the group that you want to see as a quotient in this case, you can vary the presentation, you can vary the small cancellation coefficient. We will see in the tutorial explicitly. And the choice of the small cancellation words are not necessarily, they do not have to be necessarily like this. There could be other type of choices as well. Okay, now the question that we want to move on to is, can we generalize these notions? We understand that so far we talked about small cancellation. That means we have a finite presentation, and in this presentation, our relators are behaving in a certain way. They're overlapping at a small amount compared to their actual length. So, and that phenomena, that they overlap on a small portion, has consequences. That much we understand. Now, the question is, can these things be generalized? Can these notions be extended to other contexts, more general contexts? Now, if that is the question, what is the general context that we should be looking at? So, regarding that question, let us recall what we started with. What we started with was that the essential question, the essential problem in the small cancellation theory is that given a group and subgroups, we want to find conditions on these set of subgroups such that we understand this normal subgroup and this quotient group well enough, so that we can have all these consequences that we saw. Similar. Now, in line of that question, what we observe here is that in the small cancellation theory we were talking about in the last two classes was essentially about taking quotient of a free group generated by the generating set S by the normal subgroup generated by the set of relators R. So here R is generating the normal subgroup, S is generating the free group, and we are taking a quotient of the free group by R. And in the quotient group, we can see certain nice consequences if the set of relators satisfy this kind of a small cancellation conditions. So if we have to generalize, what in which direction can we generalize, extend this notion of small cancellation? Because small cancellation was essentially it involved the relators, subwords, pieces. So in which context can we generalize it? We can we can quote Gromov here. He mentioned once in one of his articles that the freedom in the context of this small cancellation theory, that the freedom of G is not indispensable. What does that mean? Here, uh, in light of this question, that given a group G and subgroups R1, R2, Rn, we want to find conditions on this collection such that we know this normal subgroup well and the quotient group well. Now, in our presentation, G as SR, so when we say G is SR, that is Fs mod this, right? And when we say that this presentation satisfies C prime lambda, then that is essentially a property of this. And what is this? Now, if I say R is, it's a finitely presented group. So if I say that R is R1 up to Rk, then this C prime lambda property about capital R is essentially a property of this set of words R1, R2, Rk. But this set of words, as we talked about earlier, and as it is mentioned here, sorry, as it is mentioned here, that here the words, the relators, they actually correspond to the cyclic groups, right? So in light of this question, we are looking at properties for the cyclic groups, and they satisfy C prime lambda. We can see it that way. We can just reinterpret the definition of C prime lambda in the context of this question, that these are properties actually pertaining to the cyclic groups generated by R1, R2, Rk, and so on. Now, if these cyclic groups were satisfying that property C prime lambda, then we we got certain consequences regarding the quotient. The quotient is hyperbolic, quotient has linear isoperimetric inequality, etc. We had a lot of consequences. Now, if we have to have such consequences for more general context, where shall we look for? That is the question. And in that regard, Gromov says that the freedom of G is not indispensable. Now, what does that mean? Freedom of G is not indispensable. That we may not necessarily have to work with a free group. And here in the question, we don't say G is a free group. So then if we replace a free group with something else, what should it be? Now, as we know, maybe from the other courses that you have seen in this workshop, that free groups, the hyperbolic groups have a lot of similarities with the free groups, large scale similarities. They have a lot with the free groups. So keeping that in mind, if we want to extend these definitions to hyperbolic groups, word hyperbolic groups, what would it look like, and how can we generalize this? So essentially, we will be looking at generalizations of small cancellation uh, properties, small cancellation conditions today, to a few different contexts, like over hyperbolic groups, and then to more abstract situations like something called a graphical small cancellation. And possibly in the next class, we will see some applications of these conditions, the small cancellation, the generalized small cancellation conditions over these other classes. So the first one we will talk about is over hyperbolic groups, and this generalization is by Olshansky, and what he does here is he more or less followed the metric small cancellation condition C prime lambda in the same spirit of the definition for free groups, for the free group quotient, the classical small cancellation. So what does he say? He says that if we have to extend the small cancellation condition over a hyperbolic group, what is the first difficulty that we face? What was the situation for a classical small cancellation? That we had a quotient of the free group and our relators. So what was the C prime lambda condition? That we have two relators, and these two relators, they meet at the boundary over some subword, right? So these two relators, R1 and R2, in this situation, they were meeting along a subword, common subword. And where was this happening? This was just happening in the Cayley complex of the presentation, right? These are the two relators and they are meeting along two extended edges, if we may call them. So these are essentially the pieces, right? Now, then these pieces were just subwords of R1 and R2 both, and we measured the length of this subword and compared it with the length of these relators Ri's. Now, if suppose we want to do the same thing over, we want to do the same thing, but now not over a free group, but over a hyperbolic group, an arbitrary hyperbolic group. Suppose we call it G naught. So G naught, the hyperbolic group G naught, suppose we denote it with this, we give it this presentation, say call it, so G is generated by S and it has relators R. So G naught is generated by S and having relators R naught. Now, if we just want to copy whatever we was doing here verbatim to this context, what do we have to do? What were we doing here? We took some subset R, we took a subset R of Fs and then generated the normal subgroup with R. It's a normal subgroup of Fs and then took the quotient. So if we have to do the same thing, we will do what? We will take a set. So we have taken R naught. Suppose I take a subset R1 of, here it was Fs, now I will take G naught. So I will take a subset R1 of G naught, and then what will I do? I will take the normal closure of R1, and this will be a subgroup in G naught, right? So suppose I take this subset and construct and consider this normal subgroup and then go to the quotient. So if I go to the quotient, what is the first difficulty that we face if we want to talk about the small cancellation conditions? Can anyone identify what would be the first difficulty that we will face? So here the difficulty that we are talking about is we won't anymore have this kind of a situation that we had here. We won't have a situation like this. Why? Is that clear? See, what would be a piece? What was a piece? A piece was a subword that was appearing in two different ways, in two different elements of the symmetrization, right? That was a piece. Now, if we want to talk about such a piece, suppose we have taken R1 to be a symmetrized subset of G naught. So it is cyclically reduced, all cyclic permutations of all these things and so on, right? Now, R1 is a symmetrized set of relators. Suppose I take two elements from that. One is R1 and another is R2. Can I say that R1 and R2, if have they may have common subwords like this, where R1 and R2 both are coming from, sorry, where R1 and R2 both coming from capital R1. So can we always say that this will happen?
There may have bygone, right? And
What kind of bygone?
when you are in geodesic, I mean, you are in hyperbolic group, and the symmetrized word are geodesic words, right?
Yeah, so these are geodesic words. Thank you. I forgot to mention that. So here it's written. So these are geodesic words. These are symmetrized set of geodesic words. So yeah, what kind of bygones do you mean?
I mean, so R1 is there and R2 is there. They are representing identity. So
Yeah.
the common portion R1 goes through one path, and for R2 it goes through other path.
So you mean a bygone like
Yes,
this?
yes, yes,
Yeah, there could be bygones, but why are you restricting it to a bygone? Bygone means these are common points, right?
yes, yes.
They may not, these two may not even have these two common points, right?
Okay.
So the question I'm essentially coming to is, if we have to have a piece, then we have to have these words, our eyes, to have some overlap. If they do not have overlap, can we talk about pieces? That is really the situation. So more generally, what you mentioned is a bygone, so it is like this, but more generally, we may have a situation like this. That these are two different relators, but they do not have, they are coming close maybe, but they do not have overlaps. But instead, they have this. You mentioned this, I just opened up these two vertices to four vertices, right? I opened this up to two vertices, one here, one there, these to two vertices, one here, one there, right? And then it becomes something like this, right? And this is that intermediate region. You see, we have drawn something like that here. Now, what does that essentially mean? You see, what is the quotient? Quotient is of G naught. Now, what is G naught? G naught is S and R naught. Then if I take a quotient of G naught further with R1, then if I call this group to be G1, G naught quotient by R, quotiented by R1. So if I call this G1, then what would be the presentation of G1? What would be the presentation of G1? It would be S. Okay, generating set would be S, right? The same thing. But what would be the set of relators? For G naught, we had R naught. What would be the set of relators for G1? If G is Fs mod Fs quotiented out by normal subgroup generated by R, then what is the set of generators for G? We call that R, right? So what is the set of generators for G1? If we had Fs here, we would have called that R1, right? That the generating set of the relators of G1 is R1. But we don't have free group on S here. We have instead G0. So what should I write here? We have the relators from G0, which is R0, and we have these new relators R1 coming in, right? So both R0 and R1, they will be relators here, and we will take their union, right? So for the group G1, the set of relators would be R0 union R1, not only R1. That is the first difference that we encounter and kind of the source of all other differences. Okay, so now the situation is quite different because we may not have between two relators, we may not have a picture like this. Two relators may behave like this. They are coming close, they are coming quite close maybe here, but they are not overlapping. These two are not same subwords. So how to capture that kind of a situation? How to say that even here we have something called a piece. I mean, the idea of piece can be generalized here. What would be such a generalization? Can anyone say anything about that? You see, what we are doing here is finding a piece means finding two different presentations. I mean, finding two different elements from the symmetrized set, right? R1 and R2, such that R1 is U. If U is the piece, then R1 is U V1 and R2 is U V2, right? So essentially getting two distinct elements from the symmetrized set such that they can be written like this. So these are essentially distinct, right? But the prefix is same. If that happens, we call that to be a piece. We call U to be a piece if that happens. Now, what would be the right replacement for that fact, for that definition in this case? What shall we call a piece? Because they are not necessarily overlapping. What will be a piece in that case? So Olshansky generalized a piece to something called an epsilon piece. And what is an epsilon piece? He called this to be an epsilon piece. This subword, call this U subword, say call it U1, subword of R1, and Olshansky called U1 to be an epsilon piece if there exists another element R2 from that symmetrized set R such that R2 is U2, R2 is U2 V2. Now U1 is a subset of U1 is a subword of R1 means R1 is U1 V1, right? Now the condition is saying that we will find another element R2 from R such that R2 looks like U2 V2. Okay, now this is U1 and the complement you can think is V1, and if this U1 has to be an epsilon piece, this definition is saying there has to be an R2 such that this subword is U2 and the complement of that subword is V2, suppose we say, such that these two endpoints can be joined with two small words, small in the sense that the length of these words would be smaller than epsilon. Okay, now you see that we are getting here, we are getting something like a rectangle, right? Something like a rectangle or a quadrilateral of some sort. So here what the condition says is that if we can, given U1, it will be a piece if we can find an R2 with a subword U2 such that these vertical segments that you see here, if you call them Y and Z, something like the Olshansky has mentioned in this way that if this diagram can be described as U, Y, U prime inverse Z, right? So U, Y, U prime inverse Z. So that is essentially the boundary of this rectangle or quadrilateral, right? Now, these two sides, the vertical, the small sides in this picture, they have what looks small here are actually small. So what does that mean? That means Y and Z, they should have small word length, right? Y and Z have to be less than epsilon. If that happens, we call U1 to be an epsilon piece. Now, is that somewhat understandable? Any question?
So this
Anyone? Any
new
question?
thing,
Sorry?
is C prime epsilon rho.
Sorry? Obhijita, you are saying something?
Yes, yes. Just 1 minute.
Uh,
So this new thing by Olshansky,
yes.
that will give you again this hyperbolic proof.
Yes, and what he is saying, I mean, this new thing means we have so far only defined a piece. Now we have to define something called a small cancellation condition, right? And
Right,
that
right.
is not so difficult because if we have a legitimate replacement for a piece, then we can just copy the definition we had seen in the free group situation. That is a piece is less than lambda times the length of the relator it appears in. So U1 is still a subword of a relator, right? So R1 is coming from the set of relators, this thing,
Hmm.
the the prospective relator. I mean, those symmetrized set of geodesic words in G naught by which I will take a quotient of G naught. So R1 is coming from there. U1 is a subword of R1, small r1. And if that is an epsilon piece, which means I will have another element R2 from capital R1, such that it has a subword U2 with these properties that these vertical sides, like in this picture, here it is U and U prime, like U1 and U2 here. So the vertical sides are less than epsilon. Okay, if that happens, we call it an epsilon piece. But see, we while talking about the small cancellation condition, we mentioned C prime, epsilon, rho, and lambda, right? So
Okay.
rho is this parameter that we want all the symmetrized geodesic words that we have taken to be sufficiently long. Okay,
Hmm.
so we want all of them to be at least rho. uh, the reason for choosing that is, you see that in this case, this was a relator, right? Or
Hmm.
in the construction, this was part of a relator. I mean,
Hmm.
this was the star. So we see that this is not, I mean, say, I wrote somewhere, I forgot. That if I write AB, AB square, AB cube, this much is not a small cancellation word. I mean, it is not small cancellation 1/6. So I have to take sufficiently long word in order to get the pieces smaller compared to the word length. So I need this word to be long enough, right? So what are these what are these small r's doing here? The small r's are elements of capital R. What is capital R? That is the prospective set of relators, right? I will be
Hmm.
taking quotient with that. So the same way, if I want to have some sort of a small cancellation property in my quotient group, then I would like the relators to be long enough so that pieces are the pieces can be smaller compared to the word length. Okay, so that is essentially the reason behind taking all these geodesic words to be at least of length rho. So rho is a parameter in our definition in that sense. And
No, no.
yes,
Can you just repeat the argument? Why are you taking? I mean, I didn't follow.
taking what?
Taking the all geodesic words to be some
So
sufficiently words.
see here, what we were taking in a small cancellation presentation, if we had to make the presentation with this kind of words, see these ones, what we always were saying that if R is sufficiently large, then the above presentation satisfies C prime 1/6, right? Even here, uh, I mean, generate the group with this and define relators such that they satisfy C prime lambda. How do they satisfy C prime lambda? If we have large small cancellation words star,
I
right?
mean, to generalize the idea, or you need in the proof also that geodesic length has to be.
Yeah, yeah, we will need in the proof as well
And
these words to be.
okay,
Sorry.
and okay, I got the point. Okay, fine. And if there is no epsilon piece, then still we can get the quotient group G1 to be hyperbolic, right? If there is no such piece,
No, if there is no such piece, then what is the small cancellation condition?
oh,
I
I see.
mean,
I
small.
mean,
What is the small cancellation condition? Tells us that if we have a
oh, I see. Yeah.
piece
Then this.
that satisfies this condition, then we say it is a C prime 1/6 group, and then we say all the other things that we can say,
Okay,
right?
and suppose vacuously, then can we say something vacuously true that there is no piece? I mean, what I am saying, suppose you have
I
a
don't think so.
you
Yeah,
have a
please go ahead.
calligraph of this delta hyperbolic group, right? I
Yes.
am considering sufficiently large geodesic segment, and they are far from one another.
Okay.
Okay, and now I'm questioning out these all geodesics.
Okay.
So then, can you say something about that group?
A priori, I don't think it should be. I mean, we would be able to say all these things we can say in this situation, in the Olshansky-like situation, uh, because what we are doing is we are invoking the same kind of arguments that we had in a free group small cancellation. Just the problem we have is we between these two we may have other. So what is this red region in this picture? So in this picture you can see the rectangle in red. So what are those what is that red space filled with? You see that the red space must be filled with, like it's mentioned here, that this is called a contiguity diagram. So this diagram, the rectangle, is called a contiguity diagram, and the diagram is tessellated only with R naught relators, right? So what you are saying, that if I take two geodesics which are far from each other, that the space in the Cayley complex, the resulting in of the resulting quotient, the 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 two induced relators now which are giving me disks, right? They will give me disks in the resulting Cayley complex of G1, right?
Uh-huh.
Right? So I'm looking at the universal cover. Say, take the Cayley complex and the universal cover. So there, So these things, they will have some space in between, right?
Yes, yes.
So what is that space filled with? That space is filled with are not relators. Are not relators also behave in a certain way. We know some things about those relators because G naught is given to be a hyperbolic. But now we are claiming something more. We are claiming G1 is hyperbolic or not. So we need to ensure that G1 triangles are slim and G1 geodesic triangles are slim. Or I mean, G1 displays other properties like small cancellation groups. How will those be satisfied if we do not enforce anything on these things?
Okay, I see.
You understand?
Yes, yes.
So the point is, yeah, what you are asking is partly true because we are also not saying much about epsilon, right? So there will be a choice of epsilon. There will be a range of choice for epsilon, right? You cannot take epsilon arbitrarily large, right? That makes no point,
Yeah,
right?
yeah. Mm-hmm.
So you have to take epsilon suitably small as you can take, because otherwise if epsilons are very large, then there is almost no point talking about this. So epsilons will depend on on the other choices of the parameters. Say how long you are taking the geodesic. So if you are taking the epsilon to be more than the geodesic length of the geodesic, then there is no point, right? So given these choices that you make of epsilon and rho, if your pieces, the way we have defined, are suitably small like this compared to the words on which they sit, we call this presentation of G1, this presentation that G1 is generated by S1 and relators are not union R1. So this presentation, if it satisfies C prime, epsilon, rho, lambda, then it will be a hyperbolic, delta hyperbolic group for some delta. And since we said that the initial group was delta not hyperbolic, we are saying this that this group G1 is delta 1 hyperbolic. And this is the theorem of Olshansky, where he says that we can extend the small cancellation condition, the metric small cancellation condition, by going to the epsilon pieces from the pieces and defining the same condition there, like this. So I'm not going into the proof of Olshansky's result, that how he actually proved that the group is hyperbolic. Instead, uh, okay, so I will I will come back to this generalization, that one done by Delza. I will come back to that after a while, maybe if I have time. Otherwise, I'll do that in the next class. But suppose we understood
I
the
have another question. I mean,
yes.
okay, so there, okay, so here if you have a hyperbolic group, then you are quotienting to get some hyperbolic group, right?
If it satisfies
In
the
some condition, yeah.
condition. Yeah.
And there I have Rip's construction. What he has done, I mean, if you have a finally presented group and you have some hyperbolic group whose quotient is this, right?
Yes.
So I want to go some other way around. I
Like.
mean, like, okay, so suppose I have some finally presented group I have given.
Mhm.
I know that that is not hyperbolic.
Mhm.
I want to make some quotient to get hyperbolic.
You want to take a quotient of some arbitrary finitely
I mean,
presented group.
in some sense, not only, I mean, trivially. I mean, can that be a
No, so see that your finitely presented group may not have many quotients, right? So you see that if you suppose you have, what you're asking essentially is, if I have a group G which is finitely presented, right, and you want to, and this is not hyperbolic, and
Yes.
you want to take a quotient of this, suppose to G bar, and you want G bar to be hyperbolic,
Yeah,
right?
in some legitimate way,
In
not
some sense,
trivial. Yes, yes,
in
Yeah.
some sense you want to take a quotient which is hyperbolic,
yes,
but
So we have to be careful. I think, suppose this R, when you are starting it in that relation corresponding to Z cos Z, it also
yes,
survives in G bar, then it will be in trouble,
yes, yes. That
yes.
right?
So
So we
those
have to be
boundary situations are there. Suppose he can manage all those situations, all those boundary conditions. So suppose he gets one hyperbolic group as a quotient. Then this hyperbolic group will have many quotients, right? So uncountably many quotients.
yes, because of SQ universality, right? Or
Right.
okay,
So in that sense, this group will also have to have uncountably many quotients, right?
I see. Okay,
That is not true.
okay, I got the point. Okay, I think so. If G1 has uncountably many quotients, then G also should have uncountably many quotients, right?
Yes, but that is not necessarily true for an arbitrary finitely presented group G.
Yes, yes. I think, yeah. Okay, okay, I got the
I
point.
so for example, if I take just start with Z cross Z, okay.
Mhm.
So uh, okay, so maybe what I can do. So S is AB.
Shall I write for you?
Yeah.
Uh,
So the starting group, not Z cross Z exactly, maybe
Okay.
star Z, P product of Z2 and
Okay. Star Z.
okay. Uh, so this is clearly not hyperbolic. Okay, and now so in G1 also Z2 corresponding to Z2, that thing is also surviving, right? How do you kill that?
No, which G1? Sorry,
This is your G naught.
this is my G naught.
Ah,
You are asking me,
yes. So this is your G naught. So the
but
presentation is
G naught, G naught. I started with a hyperbolic group, right?
no. What I'm saying with this Rakesh question.
Regarding Rakesh's question. Okay.
So the presentation of G naught will be generated by uh, it is generated by A B C, and it's a one related group. A
Mhm.
B A inverse,
Here.
A B A inverse, C inverse, right? Commuted. And what will so you want uh, so G1. So this yeah. So R1 you have to define city value, right? So for instance, if I take just kill the
No, what are you broadly? What are you suggesting that that a given finitely presented
so what
group
will be
may
your
not?
choice of R1 to make it
And
hyperbolic?
yes, he is saying about how to kill this J2.
Oh, okay, okay.
That is his point.
So then, yeah, so how to kill this Z2? So then we have to kill
Suppose
the generator as
I
well.
send I send the entire Z2 to one. That is one trivial way,
That
right?
is, but that is
But
different.
it is also, it's possible here because you have another Z available. If you did not have this, then there is no other way but to sending it to the trivial group.
No, you can do it. I mean, you send make one of the generator to be one. Z is
Okay,
a
okay,
quotient of Z2,
yeah,
right?
okay. So you take a Z quotient. Fine. Yes.
But is this only way? I don't know.
No, but
Yeah,
I think in general the question that he asked would have a negative answer.
yes, yes,
I
right.
mean, So what you are trying to say is you are trying to get a method of getting the map when the answer is positive.
Correct. Correct.
There is a positive answer because you have to kill all those J2 or if I mean some trivial
Yeah.
way. But I want some legitimate way. I mean, not the trivial or not to killing those kind of thing. Some sense of.
So I don't know the answer. See, the way I said that it won't happen is it is not SQ universal. So not necessarily SQ universal. But I don't know whether if you assume that your group to start with is SQ universal, what can be said. That I don't know.
Yeah, I mean, I got the point. Okay.
Okay. So coming back to so I can continue for some more time, right?
Okay. Yeah.
Vijita? Can I continue
Yeah.
for say 10-15 minutes?
Okay. But you can do it in tutorial time also. Some time you can take.
Oh, okay, okay. So in the beginning of the tutorial, I will speak for a while and then Partho can do it.
Yes. Yes. Yes.
Okay. So shall I stop here now?
Yes. Yes. Yeah.
Okay. Okay. Thank you. Thank you. So I'll disconnect all this.
Uh,
I mean,
let it
should
be
I